All right, in this video we are going to look over a pretty amazing little section of the urinary system called the juxtaglomerular apparatus. Now earlier we talked about autoregulation, and we talked about how the kidneys they control themselves basically, and some of the different mechanisms, the autoregulation and the sympathetics going to decrease the production of urine. We talked about how there's a cycle with this Renin-angiotensin or tensin system. We'll talk about that at another time, and or actually we're talking about that right now because of this thing renin. And then we also talked about the atrial and the ventricular nitritic peptides. But again, this is the main thing we're going to kind of talk about in this. So this is the renin-angiotensin system, and renin is produced by the kidneys, and it is the start of this cycle. We're going to look at this substance called angiotensinogen, and again, I think everybody's familiar with the fact that if you see OGEN on something as that's ending, that means that eventually that's going to be cut off and you're going to have what the root word is. So renin is what cuts that off and produces, makes this inactive molecule called angiotensinogen and turns it into this thing called angiotensin 1. Right? Now again, I'll go through the brief cycle since I've already started it, but angiotensin 1, when it goes through the pulmonary system into the lungs, it will come in contact with this thing called angiotensin converting enzyme. It is called ACE for short, ACE, angiotensin converting enzyme. And it converts angiotensin 1 to what will then be called angiotensin 2. So people that are dealing with high blood pressure and are taking medications to bring it down abnormally, our body will recognize it as a lower than what it wants to have blood pressure, and it will start this cycle. And so they'll take what are called ACE inhibitors, which make this inactive, and therefore angiotensin 1 can't be converted to angiotensin 2, and that helps control the blood pressure. And again, now the blood pressure, while we're looking at it from the outside looking in, this cycle is designed to raise blood pressure when blood pressure has dropped low in a bad way. So to read through this, the renin-angiotensin system responds to a decrease in blood pressure through vasoconstriction, squeezing the blood vessels, which we know is going to increase the pressure, and the secretion of antidiuretic hormone, which means I'm conserving water, which again, if I'm pulling water into the circulatory system, that's increasing pressure, as well as aldosterone. And aldosterone works on sodium ions, and when it pulls sodium ions back in tubular reabsorption, the water is going to follow the sodium ions, and so that's going to help increase blood pressure. All of these things go to increase blood pressure. So just kind of looking at this, and angiotensin 2 does all kinds of things. Again, the things that we just listed here, increased aldosterone, increased antidiuretic hormone, and it's also going to flip the switch to make you thirsty, because again, I can drink water, increase blood pressure. So the way that it starts is with this really special thing called the juxtaglomerular apparatus. And again, we looked at juxta means close to or alongside, and glomerulus or glomerular means the glomerulus. So it's this area that's close to the glomerulus. And it is what regulates the secretion of renin that we just looked at, that is the trigger to start the chain of events. And so if we have just a brief little, kind of simplistic drawing of, a nephron, and so I've got this nephron loop, and then we have the ascending limb, and then it goes back to the distal convoluted tubule, and then it's going to, connect to this collecting duct, right? So what's going to happen is this little area here isn't very far from that. It actually is going to be right in between the, I'm going to draw a little arrow here as the afferent arteriole, and this coming around as the efferent arteriole. This spot here is actually going to be found right in the middle of this. So we'll see it better on the next picture. But at this point, the ascending limb comes in contact with the afferent arteriole, and it's going to form the juxtaglomerular apparatus. And there's two areas that you need to know. One is called the macula densa, which are cells that are are associated. They are part of the ascending limb. And then these that are called juxtaglomerular cells, and they're actually part of the afferent arteriole, right? So those two are going to work together, and you'll see the next picture. I want to show you one that's a little more close up, but I just wanted to use this picture so you can kind of see that's where I'm talking about. So proximal convoluted tubule, this is basically the nephron loop with the descending and then the ascending limb, and then this is the distal convoluted tubule. But what happens is the ascending limb, right before it makes this turn, it's going to come in contact with this afferent arteriole, and that's what we're seeing in this picture. So I'm going to go to the next one so you can see it better in a close-up. So this is the one a little close up, and you can see these cells, which are part of the ascending limb of the nephron loop, are what are called the macula densa, and then the juxtaglomerular cells are the specialized smooth muscle cells that surround the afferent arteriole. And so those together, those two things together, form up the juxtaglomerular apparatus. And so when we look at what the nephron loop does and how it works, it's going to make a little more sense. But basically, as the fluid, so I've got filtrate that's coming out of the glomerulus. It's going to go into the proximal convoluted tubule, and most of the things are going to get reabsorbed there. Most of the water, the glucose, the important things get filtered there or reabsorbed. And so I've got this nephron loop, and in the nephron loop, this is what's going to happen. There's going to be a volume control, and when I say volume, not loudness, but the amount of urine that's produced. So if I look at, let's say for just ease of argument, I have 10 liters of fluid with 10 grams of sodium that enter the descending limb here. Now the descending limb, we're going to find out, is permeable to only water. So water is going to be pulled out as it goes down here. And so at the bottom, we'll say that now it only has 1 liter of fluid, but since there's no ions that got pulled out, I still have 10 grams of sodium. All right, I hope you're following me on this. And again, these numbers don't mean anything. I'm using them just because they're easy numbers to see. Now, as it makes the turn and it goes on this this ascending limb, the ascending limb is not permeable to water, but it is permeable to ions, especially sodium. And so sodium gets pumped out. And so when it reaches the top part of the ascending limb, right before it's going to go into the distal convoluted tubule, right? This area right here, right at the top, should have the same basic concentration as at the beginning, just the volumes decrease. So you would have 1 liter of fluid and 1 gram of solute. So it's still the same concentration. 10 liters and 10 grams is the same concentration as 1 liter and 1 gram. And so these cells, these macula densa cells, they're watching the filtrate as it's going up through here. And they know the concentration it's supposed to have. And so let's say I know that for every 1 liter, I have 1 gram of the solute, right? And that's normal. So let's say that this fluid is going faster than normal. And if it's going faster than normal, when it's going through this ascending limb, it's not going to pull out as much sodium because it's going to be moving too fast. And so at this point, I'll still have about 1 liter of fluid, but I'll end up having, 2 grams of sodium. And again, these aren't the real numbers. I'm just, looking at it. So it's going to know, man, this fluid is going too fast. So in order to control the filtrate, that means that the blood pressure is high. Right? Does that make sense? So, because if the blood pressure, remember the force of filtration and the filtration rate is the main force is the glomerular hydrostatic pressure, the blood pressure in here. So if blood pressure is high, it's pushing out a lot of filtrate, which is going to be moving too fast through here, and I can't do the job. And so these maculodensa cells will reach back to the juxtaglomerular cells and cause them to vasoconstrict. They close down a little bit. This limits the pressure that is going to be in here, and it is going to start slowing things down. Now, let's say it's the opposite. Let's say instead of it going too fast, let's say it starts going too slow. And if it's going too slow, now this ascending limb can start pulling too much out. So all of a sudden, I don't have 1 gram. I have, I'll say I have, 50 milligrams. All right, so half of a gram, we'll just say. Right, so, and that doesn't look right there. But anyway, you know what I'm saying? It's pulled out too much. So again, these guys right here realize, wow, there's it's too dilute. There's not enough filtrate. So they know that means that the whole thing is going too slow. So instead of worrying about this, trying to reach back and do anything here, which it will a little bit, it'll cause it to a little vasodilate. What it really is going to do is it's going to release that substance called renin, right? So renin, which, man, that is a terrible look for it. But renin, what we just looked at, and I'm not going to try to spell it now, it's down here. Renin will be released, and it's going to cause a chain of events. It's going to cause more fluid to be reabsorbed, which is going to increase my blood pressure, and then in turn start increasing the filtration rate and speed things up. That's basically how this works. So it's going to help regulate blood pressure in 2 different ways, and it's really going to be working on just the simple knowledge of, at this point right here in the system, I should have a set concentration level. If I know that it's too concentrated, that things are moving too fast, and I need to do something to slow the system down. So I'm going to vasoconstrict. That drops the pressure in the glomerulus, therefore it slows the filtration rate, which is slowing the filtrate. If, on the other hand, at that point, I see that the system is too dilute, that it's pulling out too much, that means it's going too slow, and then I'm going to release this renin. And by releasing renin, I'm going to start a cascade event that's going to cause the conversion of angiotensinogen to angiotensin 1 that goes through the lungs. It comes in contact with the ACE, the angiotensin converting enzyme, which converts angiotensin 1 to angiotensin 2. And then angiotensin 2 will have a ripple effect that's going to cause antidiuretic hormone to be released, causing more fluid to be reabsorbed, aldosterone to be released, which is going to cause more sodium, therefore more water to be reabsorbed. Both of those increase the blood pressure. It's going to cause a thirst reflex, which is going to cause you to try and put more fluid inside your body to bump up the pressure. So all that's how it's trying to regulate, which it's just, to me, this is an amazing area. Again, all of this is set from the DNA from the first 2 half cells that get together, and how to create it, how to build it, how to maintain it, and how to use it is all stored in that one strand of DNA. So now we go back to this and kind of put it all together. So I have the the nephron that's going to be going through and filtering things. I got the proximal convoluted tubule. I've got this nephron loop. I've got this special area of the ascending limb of the nephron loop before things get crazy again. This area here, which is actually going to be, over in this area. If the filtration at the filtrate at that point is too dilute, our body knows that something is going on with the pressure. The filtration rate is dropped, and that is generally one of the main things. Is it's a response to a decreased blood volume, a decreased blood pressure, which is a decreased blood volume. So this is going to release renin, which will take angiotensinogen, convert it to angiotensin 1. Angiotensin 1 will go through the lungs and come in contact with this angiotensin converting enzyme that converts it from angiotensin 1 to angiotensin 2, which angiotensin 2 will go through. Part of it's going to cause the blood vessels to vasoconstrict, increasing blood pressure. It's going to cause aldosterone to be released, which is going to pull in sodium, and water is going to follow, which increases blood pressure. It's going to increase the antidiuretic hormone, which is going to be pulling in water directly, increasing blood pressure. And finally, it's going to increase thirst, which is I'm going to put more water in my body, which is going to put more water in the circulatory system, which is increasing pressure. So that's how it works, and it helps keep things in order. Now this slide, I put on this portion of it. I'm not going to get into too much on this. I do want you to know there's a couple things. First, this shows the concentration in plasma, the filtrate, and then urine. And so as it's going through plasma, it is going to be pulled out in the filtrate. It's generally going to be close to the same in all of these cases. As a matter of fact, it's exactly the same in every one of them. But as this filtrate goes through the proximal convoluted tubule, the nephron loop, and then the distal convoluted tubule, and finally get to the minor calyx where nothing else is done to it, and at that point it is urine, there's going to be all kinds of modifications. You can see that the sodium that enters, there's going to be sodium that is reabsorbed. Now potassium, you see there's not much that in potassium that is filtered, but a lot of potassium is going to be excreted by the way of tubular excretion. So it is, or secretion, it is going to be put, it might not be filtered, but it's going to be put from the blood vessel into the tubule. Calcium, a little bit is going to be put out. Magnesium, a lot of it, a good percentage of it. Chloride. Now we get to some of them bicarbonate that's actually going to get pulled back in. Now these two, these are going to be tubular secretion. So the majority of these are going to, even though I'm not going to filter a lot of them, I'm actually going to have tubular secretion get rid of a lot of those ions. Now on these are going to show you some that we're really going to have tubular reabsorption. So the filtrate or the glucose, almost all of it's going to be reabsorbed, and it should be all of it. If it isn't, that's usually a sign of diabetes. Urea, while it doesn't get filtered, it gets pushed out a lot. Tubular secretion here is a big deal, as well as uric acid. Now, creatine, this one I think there's a typo, because generally creatine is not going to change. Now it might be the way I'm looking at this, because creatinine, I should say, is what we use as a measure for renal function, and so anyway, I don't want you to worry about these values right now. We'll explain what creatinine does a little later on. I just kind of wanted to show you the difference of what's going on and why there's certain things that are standard that that little juxtaglomerular apparatus is going to monitor, particularly with sodium.